So let's move forward. Cryptographic protection of machine learning models. As Vlad mentioned, my name is Anastasiia. My nickname is Vixentail. You can find me online in Twitter, GitHub, Facebook, LinkedIn, yada yada yada. And I am security software engineer with a background of software development. So I'm kind of in between the worlds of software development, applied crypto, security engineering. I work at Kozak Labs. Kozak Labs is a UK/Ukraine data security company. We are a product company. We create tools and solutions for data protection. Some of our tools are public, free, and open source. You can find them on a GitHub. Some of our tools are paid and closed source, proprietary. We take part in a lot of cryptographic R&D, like research, with novel cryptography, as well as use pretty boring standard cryptography to solve problems of data leakage and complying to regulations. Okay, typically we work with companies that value data security a lot, no matter of their industry, right? Critical infrastructure, fintech, neo-banking, machine learning, even just popular mobile applications. All of them are good enough for cryptography if they take care of take care of sensitive data, right? No matter what kind of data it is, rather user passports or machine learning models. And the second one we will go to talk about today. First of all, the disclaimer slide, okay? This is the most important slide on this presentation. Things that we won't talk about. Because I know. Machine learning is a nice term, it's like hype, artificial intelligence, machine learning, la la la. So we won't talk about adversarial networks and adversarial attacks. So we won't talk how banana sticker creates banana into toaster, things like that. Sorry, if you're interested in that, follow the link. We won't talk about machine unlearning. By the way, someone on Twitter suggested this topic to me and I read the paper. This is fascinating. So you can basically make the model to unlearn some things. I really like the idea from privacy perspective, but no tackling it today. Read the link. Number 3 is a malware inside machine learning models. Obviously, you can kind of put some custom layers and kind of hide malware in your model. We won't talk about that today. And of course, the news of the latest days, the bug in TensorFlow in YAML serialization. We won't talk about that today. Yes, sorry, not the topics of today. This is a cryptographic talk. No fancy things. What we will talk is cryptography, a little bit of TensorFlow, a little bit of IP protection, intellectual property protection, right? We will name things like application level encryption. We will name things like HPKA, hybrid public key encryption. And we will, of course, speak how to integrate cryptography into real world, into other traditional security controls, right? We will speak about API protection, cloud security, mobile application security, anti-reverse engineering, and anti-fraud. Okay, so if you want to hear about that, okay, stay on YouTube. If you want to read about fancy things, just follow the links. And obviously, I will share my slides afterwards, so all these links will be available for you to explore. And I really encourage you exploring things. Let's move. What is our case for today? Imagine, totally artificial case. No name dropping, no company names. Imagine that you're a large company and you work in machine learning space and you create mobile applications, Android and iOS applications that work with this machine learning models. Right now, you have a huge model on your backend, right? On your backend side that serves requests. So your mobile applications make requests to your backend. Your backend use machine learning to create response and send it back to your mobile applications. However, you have really a lot of users, millions of downloads. You pretty popular in the App Store and Google Play Market, right? So you would like to decrease a load from your server side to your client side, basically to put some pieces of this huge machine learning module to the client side, to the application side. But this opens totally new security challenges and threat vectors. And the case we will discuss today is how to protect these small pieces, these small machine learning models that you basically put out of nowhere, like you put out of your trusted backend to these tiny mobile applications, hundreds of them, thousands of them installed in your huge user base. So what is, as I mentioned, was before? Before, your mobile application sent a request to your backend. Your backend has access to this large, full machine learning model. It executes this request, it generates something, and it gives response back to the client side. Every time when user, I don't know, wants to see a cat picture with cat ears, right? Or like use a photo with cat ears, they send request to the backend. Backend needs to do these calculations and send response image back. Okay, repeats every time. Of course, when you have like hundreds and millions of users, this is a little bit complicated. So you want to change that. You're changing the scheme. Now, application send request to your backend. Instead of creating a ready response, your backend creates small individual machine learning model, and send it back to the client side. And then client side executes this machine learning model. So instead of creating hundreds of images on the backend, you put this load on the client side. Now your client side, your mobile application, is responsible to create these nice images of people with cat ears. You know what I mean, right? So, and these individual machine learning models, we will call them IML during the presentation. They are unique per user. So you have hundreds of downloads. Each download is a device. Each device is a kind of user, and each user can have a lot of these models. But you don't need to make requests every time user wants to see a picture of them with a cat ear, with the cat ears to the backend. So sounds good. What kind of security risks it opens from business perspective, this switch? Obvious, like advantages are obvious. You change the load from your backend to the client side, and instead of paying for the cloud computation, you make mobile devices of your users to do these calculations, right? All good. However, what is the risk? Obviously, the leakage of IP, because when you put these small machine learning models to the client side, you basically kind of cut your large model and you put the sensitive bits of information for hundreds of applications that you have, right? And things like competitor advantage. If your competitors will steal those small models, and if they understand how it works, they can recreate the same model and they can move your application rating in the stores. So you will need to do something to change your model to involve machine learning engineers, yada, yada. And of course, like things like broken applications, cloned applications, API fraud. So when you have an API to generate those small individual machine learning models, this API can be abused. And we don't want that because it means abuse of infrastructure, potential denial of service, potential loss of revenue, and of course, losing, leaking, and abusing the IP. All the things are about money. So it makes sense to invest a little bit to protect those tiny individual machine learning models. Now, how to protect them? Let's dig into cryptographic, let's dig into technical stack that we have. As I mentioned, we have mobile applications, and in this case, these are nice and native mobile applications. Objective-C, Swift, and CoreML framework on iOS side, Kotlin and TensorFlow Lite framework on Android side. Nothing fancy, very native. And we have a cloud side and a backend. Technically, this technology I will speak about, the protection of models itself is cloud agnostic. We don't care what cloud is it. But for the sake of example, I will use Google Cloud Platform. So on the backend, we will have Python, TensorFlow, and Google Cloud Platform services like GCE, computation engine, like workers, like storage, like Google Cloud KMS, different kind of databases, Firebase, all the nice things that Google Cloud can give you. AWS has the same, so cloud doesn't matter. Just a cloud. Moving to architecture. This is more or less how very, very high level architecture might look like. Let's move from right to left on this scheme. Let's start from the right. So obviously in your company, you have this main TensorFlow architecture where you have this large machine learning models, where you have some training services, training servers, and we don't care about this piece at all because this is not a part of IP you put on the clients. This is something that is trusted in your network, right? You try to protect that. Next, how you generate these small IMLs. You have some cloud workers, some servers that probably use autoscale, so they can spawn, they can exit, and they generate these small individual machine learning models based on some user data, based on this large TensorFlow model, and put those small machine learning models into some storage. It could be Google Cloud Platform storage, it could be AWS S3 bucket, no matter. So you generate those individual machine learning models, you put them into the storage. Your mobile application, and you do this on request. Your mobile application send request, hey, I need a machine learning IML for my user, to the API triggers cloud workers generate IMLs, they put it to the storage, API provides a link, devices download the model from a link. Very straightforward. And then devices will execute the model on device side. So in terms of IP protection, in terms of protecting IMLs, we are really interested only in this part of the data flow, right on the left. The places where IML is. And to put it in the nice table view, we can say that, okay, IML is generated on a client, on a cloud side, and it is in the memory of this worker, right? Then it gets transited to the storage and it is stored, like data at rest, stored on the cloud side. Then it is transited to the via API to the mobile side, right? And on the mobile side, it is stored somewhere in the mobile application, in some like file system or cache. And then of course on the mobile side, it gets executed. So this model appears in memory. So basically we have this machine learning model like everywhere, in memory, in transit, in storage. Sounds like a cryptographic task. Let's talk a little bit about threat modeling. Very, very simplified, okay? What are the potential threats, threat vectors and attack surfaces in this infrastructure? How these IMLs can be stealed? Obviously, using API, via leakage, via abusing. Obviously, from the storage, if you can just go and pick a link, all these cases with AWS S3 buckets, when buckets are public, when links are public, and anyone who knows the link or who can enumerate all the resources on these buckets can get access. So similar, when you store something on the cloud, on a public cloud storage, this data can be found. So it's very important to take a look on access controls. Now, transit, yes, active man in the middle, passive man in the middle. Active man in the middle might be really interesting. Imagine that you can check like you can intercept and tamper the machine learning model from its way through the backend to the mobile side and change it, right? It would be really cool to change the model, and instead of, I don't know, putting cat ears on the user faces, you can put dog ears, okay, or like cat nose. or really bad things. You can put really bad things on this machine learning model. Well, so we really care about man in the middle, passive or active. And of course, mobile applications are a huge part of attack surface because the machine learning models are get there, they are stored there, so they're subject to reverse engineering techniques. You can imagine this some kind of crowdsourcing, right? If your competitors would like to get a lot of those models, they can ask users to send those models to you. And you can also imagine different kind of cloned applications or broken applications or like malware applications that are available at 4PDA, which gives users like nice shiny features, however, have some malicious code that will send those models to their backends instead. Right, so attack surface is quite large. Threat vectors are numerous, and if we're talking about stride kind of model, we are mostly interested in spoofing, tampering, disclosure, and denial of service. And of course, cryptography won't help you a lot with denial of service, but will definitely help you with confidentiality, integrity, and authenticity of the data of these machine learning models. This was the introduction part, and I think now you're ready to basically dig into crypto part. Yay! So before we start discussing encryption of machine learning models, let's think for a second, what is the machine learning model itself? And disclaimer, I am not an ML engineer, okay? So if you're an ML engineer, you probably know things about machine learning model better than me. I am security engineer, so sorry. From security perspective, machine learning model is just a file. Okay, this is like a little bit sophisticated file because it contains some model data, it contains some like procedure, algorithm, how to get this data, right? But from security perspective, this is just a file with some structure. In our case, it was layered structure with weights, right? So the file is sensitive data, the data inside file, like weights, is sensitive data. Very simple, very straightforward. Yes, sorry, no exciting machine learning things here for you from cryptographic perspective. When we will take a look on the architecture scheme back, we will see that we can use very naive approach to encrypt data. The machine learning model is created on the worker side, on the backend side. Cool. We create the model, we will encrypt the model right after creation. We will store this model encrypted across all the ecosystem, across all the infrastructure. We want to store it in a cloud storage. Okay, no problem. We will store it encrypted as a file, right? Then when mobile application will get a link to download this model, they download the model, and then they decrypt the model. Very straightforward. And as you can see that encryption and decryption points in this infrastructure, they are different, which means that we can use public key encryption cryptography here. But before we use that, let's discuss requirements of encryption layer, because why build things that don't satisfy our requirements? As any requirements to cryptography, it should be fast, smooth, cool. It should work everywhere. It should be super easy in terms of cryptography and super easy in terms of key management. Come on, we're like application with machine learning and artificial intelligence. We don't know how to build a proper PKI, how to build a proper public key infrastructure. Can we please avoid that? Right? And obviously, cryptographic protection should solve two main challenges: to minimize lifetime of plain text models, so to store it encrypted as much as possible first, right? And the second, to avoid accumulating a lot of those small models, which means to use different keys, different encryption keys across the models. Because imagine if you have these hundreds, millions of downloads, hundreds, millions of users, and even more models. If you use the same encryption key across all the machine learning models, well, your security is not so great. So we suggest obviously to use different encryption keys, to use unique encryption keys per model. And in terms of key management, this might be tricky, but cryptography, we know things how to build key hierarchies, right? Which I will explain soon. So what we want from cryptography: encrypt model right after generation, decrypt it only before usage, use nice traditional no fancy ciphers like IS, the 56 GCM, like elliptic curve Diffie-Hellman, fast modern cryptography. Use ephemeral keys like temporary keys to avoid building complicated public infrastructure, and of course use cryptographic libraries that work across all the platform, keeping in mind all future platform you want to build. We will use Themis for this purpose. Let's see how this architecture diagram, how these encryption and decryption points will look like in a flow, in a sequence. On the mobile side, mobile application generates key pair, mobile key pair. It sends public key to the backend side, right? The step of the key exchange. On the backend side, backend application working in this example, it will generate its own server-side key pair, right? It will take public key from application, own private key, use elliptical Diffie-Hellman magic to derive a shared key, right? Then on the backend, we will generate random DEC. DEC means data encryption key. Random data encryption key. We will take our individual machine learning model. We will encrypt it using this newly generated DEC, using IS, the 56 GCM, encrypt machine learning model into encrypted machine learning model. Then what we will do with the key, because we just generate this key, we will encrypt the key, right? We will encrypt data encryption key with shared key we generated on the step 2. We will use same IS for 6 GCM. And this is what we got: encrypted model, encrypted data encryption key, and server public key. This is our package. This is our data structure. We send this package, we store it on the cloud side, and then we send it to this mobile application. Upon receiving, mobile application takes its own private key, which was a part of a key pair generated on step 1. So it takes its own private key and server public key from the package to use the same elliptic curve Diffie-Hellman to derive the same shared key, right? Then using shared key, it decrypts encrypted data encryption key, right? And using this data encryption key, it decrypts the machine learning model. Here you are. Simple, straightforward, IS, GCM, elliptic curve Diffie-Hellman. Well, of course, in cryptographic details, probably after deriving shared key, we will need to use HKDF or something like that to derive stronger cryptographic keys, but these are cryptographic details I don't want to dig into. Let's look at the code. Let's look at the format first. So this is how model machine learning model might look like, or like API response might look like. Simple JSON. You have your encrypted machine learning model, encrypted model, right? You have your encrypted key. You have public key of the backend side. Why the key is ephemeral? Because these key pairs are temporary. And because backend won't store its key pair, it just generates key pair, it uses key pair. This technology, like the approach, is called ephemeral keys or throwaway keys. We generated cryptographic keys, we use them, we don't need them anymore, we don't need to store them anymore, right? Encryption version, because this is very important to put encryption version on any encryption systems that you build, because you will want to rebuild the system soon, and maybe some additional encryption inside your machine learning model later. This is how the code might look like, and honestly, this is a more or less compilable Python code. I know it looks like a pseudocode, but it's technically, I believe you can compile it. This is all cryptographic codes that we need if we use Themis. Themis is a cryptographic library. I will talk about it in 2 slides. So the encryption part, the backend part, as we previously explained, generate key pair, generate data encryption key, temporary, right? Encrypt the model, encrypt data encryption key, and send encrypted model, encrypted key, and own public key. Decryption part, mobile part, I used Swift in example here, and again, this code. This is a code, it's not a pseudocode, this is a real code. I believe it's compilable, right? And this is all encryption code you will need in this case. On mobile side, generate key pair, take own private key, server public key, decrypt your data encryption key, then decrypt a model. Here are very straightforward, very easy. The reason why we have only like 12 lines of cryptographic code is because we use nice tools. Instead of spending time fighting with OpenSSL, we can use modern, boring cryptography library. And in this case, we use Themis. Disclaimer, like Themis is an open source library maintained by Kozak Labs team, so we use it pretty often. But of course, you can use another boring crypto libraries like Lipsodium, for example. Really nice. Just beware, because if you have a lot of platforms to support, you might want to find libraries that work on these platforms, right? Because many problems with cryptography come from different APIs of cryptographic libraries across different platforms. So with Themis, it's not the case because it's a single library that works across many platforms and it hides cryptographic details. You see in this code, you don't see these keywords like IS, you don't see the keyword like elliptical Diffie-Hellman. You don't know anything about init vector, about nonce, about key lengths, key padding, because if you're a software engineer, you don't need this kind of details. You just want things to work, right? Boring crypto, not exciting at all. And a nice thing that Themis was actually recommended by OWASP as a library to use on mobile devices when you make cross-platform application, which is cute, and which is technically our use case here. Just to introduce a new term probably in your life, the idea that I just explained, that backend and mobile applications are encrypting and decrypting data, and data stays encrypted across all the other pieces of your infrastructure. This idea is called application level encryption, right? So new term, new hype word in your vocabulary. Basically, it's just a marketing term, right? Basically, application level encryption means that this is encryption that is kind of built into application, any application, triggered by application, part of the application code, right? Obviously, it can be a library in your code. It can be a separate service, right? Why we distinguish application level encryption? Just to tell that there could be data at rest encryption in your database, for example. There could be data in motion encryption, like TLS, right? And there is application level encryption. And these 3 different types of encryption, they work on different levels. So you can have all of them at the same time. And using application level encryption means that you probably still use TLS. You probably still use data at rest encryption in your database, right? But now your applications are responsible to encrypt and decrypt data. Of course, it could be client-side, server-side, or end-to-end encryption is, in fact, application-level encryption. I don't want to talk more about application-level encryption. It has different risks and threats and provide different guarantees comparing to TLS, comparing to file system encryption or database encryption. And of course, end-to-end is just ultimate category of application-level encryption. If you're curious to learn more, please follow the article below at InfoQ. We wrote huge article about application-level encryption and different key management problem related to having your applications perform cryptographic code. Another term that you might like, and another term to your cryptographic vocabulary, is hybrid public key encryption, HPKA. So again, link in the bottom. So what is happening here? Basically, this approach, this idea is not new. As many things in cryptography, it's ancient. Just the name is new, because RFC that explains HPKE approach is quite new, and RFC explains, like, tries to to make a standard, tries to describe different HPKE approaches, try to, you know, to make a standard. So maybe in 2 or 3 years, when we will speak about HPKE, both of us will understand what it means, because right now not many people understand what it means, and the RFC tries to make it, you know, a standard. Basically, hybrid public key encryption means that you combine symmetric cryptography and asymmetric cryptography. As we did in our example, we use symmetric cipher. In our example, we use symmetric cipher authentication encryption with additional data, right? ISGCM to encrypt machine learning model itself. And then we use public key encryption, elliptic of Diffie-Hellman, derive shared key, yada yada, to encrypt the key, the data encryption key, right? And combining symmetric and asymmetric encryption is an approach called HPKE. The RFC describe different formats, different ways how to do that. You can combine different ciphers, you can combine different hash functions, yada yada. And as I mentioned, tries to make it a standard. So new term for you. Okay, let's get back to our cryptographic scheme. What in this scheme, what we achieved in terms of key management? The key management in our example is super lightweight, it's super easy, because we use these ephemeral key pairs. We don't need normal, strong, secure PKI. You know, building public infrastructure is a struggle that many companies do, especially even in security, right? So in our case, we don't build PKI. We kind of have proto PKI, because to be able to pin our users, we can store their public keys in a database, but this is very, very lightweight PKI, just storing public user keys. It's not a PKI itself, right? And obviously, as our key pairs are ephemeral, we don't actually care a lot about key management procedures explained in NIST. Yes, we care about key generation. We don't care about key rotation mostly. We don't care about key revocation, because we create cryptographic keys, we use them, and we forget about them. Easy. You don't need to revoke keys that exist 1 minute, right? Very nice approach. Obviously, it won't work everywhere. And the main burden of key management goes into mobile applications, because on mobile applications, they need to store encryption keys, and luckily they have keychain and key store to store keys. And on iOS, for example, we can even bind these keys using a secure enclave, right? So build proper key storage in our mobile applications. Unfortunately, this approach won't solve the authenticity problem. Remember our man in the middle example. If someone will steal the machine learning model and change it, our client side almost doesn't have a way to make sure that machine learning model came from trusted backend, but cryptography won't help here. We can use other security, like traditional security things like server-side attestation and tailor spinning, to make sure that device trusts the backend. Now, let's make it even more complicated, because this is just a basic layer, right? On device side, when device received individual machine learning model and decrypts it, device can re-encrypt it, like application can re-encrypt the model before storage. Very simple, just generate another symmetric key and encrypt this model before storage. Why? because in this case, this application won't need access to its own private key or backend public key, right? If this model will stay there like for months, for example, the application won't need to store all the keys required to decrypt this model if it uses another symmetric key to encrypt the model. Of course, it will mean that we will need to store yet another key, but come on, we have key store and keychain. We can do that. Bonus points if we use biometric binding with keychain, for example, with keychain. Now, next. So re-encryption on device size. Step 2 in our cryptographic defense in depth, add more cryptography to protect cryptography. As you can see from this example, the lifetime of plain text individual machine learning model is quite limited, right? In plain text, those models live only during generation, during this decryption on mobile side, and re-encryption luckily, and during execution. And the execution part, when mobile application will execute machine learning model, this execution part is complicated because most frameworks like CoreML, for example, on iOS, it requires the machine learning file to be in plain text, right? When you use API to load the model into memory, the file should be in plain text. However, we can use nice CoreML tricks to add encryption inside layers of our model, right? So all the steps before, we were talking about machine learning encryption as a file. Now, remember that these models have structure and they have layers. So we can create custom layers that are encrypted, right? And we can decrypt them before loading the model to the shader, which will mean CPU load on the mobile application. Or we can go even further and we can create custom shaders to obfuscate weights before executing on the GPU, before executing on the shader. Unfortunately, GPUs don't have a lot of memory, so we cannot use real encryption to encrypt weights in the shader itself. However, we can use different kind of obfuscation techniques, XORs, and very lightweight cryptography. Also, Apple has really nice docs that explain that you can, in fact, encrypt the file of machine learning model and explains how to do that. This is like a tricky bit, a little bit from machine learning perspective, right? So encrypt the model file itself and try to encrypt layers inside the machine learning file. Obviously, encryption means performance penalties. As I mentioned previously, GPU shaders have quite limited cache memory. We cannot run typical cipher there, so we either use obfuscation or we use very, very lightweight cryptography. In our example, we use normal, standard, like traditional fast cryptography with hardware acceleration like IRGCM, so we don't have, crypto won't take a lot of time. The thing here is if your mobile devices can run CoreML models with quite high FPS, right? So without noticeable changes for people, it usually means that your mobile devices can do cryptography really fast, right? So again, no noticeable UX changes. And generally speaking, it might be like on the back end, in generating these individual machine learning models, encrypting them, sending them, and decrypting on the client side might be faster than the previous approach this company used, executing models on the back end. So what we did here, we encrypted the machine learning model lifecycle across, like machine learning file across its lifecycle, and we did our best to cover the whole data flow. But as I mentioned previously, cryptography is kind of boring if you don't combine it with other, with other security controls. So remember, we have the scheme where we already use crypto on the backend side. We already store encrypted data on the cloud, and we use crypto on mobile side to decrypt data. And now let's put traditional security control there. Let's put authentication, API security, application security, anti-fraud, anti-reverse engineering, yada, 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 because cryptography doesn't work in vacuum. It doesn't exist in vacuum. You still need these traditional security controls. You still need to log. You still need to monitor. You still need to understand whether users are malicious or not. Let me talk really quickly about some of these security controls which are especially efficient working together with crypto. For example, cloud storage security. We mentioned this previously. If you have AWS S3 buckets, or if you have Google Cloud Platform storage, you might want to check. OWASP has a special, OWASP has a guideline how not to make configuration mistakes when you use public cloud storage. Obviously, the approaches are well known. You try to limit life cycle of the files that you store, so you don't forget to clean those files, to remove those files physically, right? You don't forget to use TTL on the URLs, like access URLs. So the URL itself will expire really quickly. And in our example, by the way, we use TTLs really small, like 1 minute or so. So the idea was that when mobile application make request, backend can generate all this individual machine learning model, put it to the cloud storage, and get it back in response under several seconds, right? So TTL with 1 minute lifetime was enough for mobile application to download the model. Obviously, authentication, access control, and what is very, very interesting that many cloud providers have backup functionality out of the box. So do your best, try not to back up sensitive data. Now, API protection. Well, you know all the things how to protect API. Authentication, API limits, request throttling, firewalling, yada, 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 yada. Just check OWASP ISPs and you're good to go. Why this is important in this case? Because API was a gateway how mobile application will get their machine learning models. Right, so yes, the cryptography of machine learning models might be nice, but if you have API without any protections, anyone can generate like hundreds and thousands machine learning models for them, which defeats the purpose of this exercise. Now, another nice thing here is anti-fraud system. Think about banking anti-fraud. Think about that you want to limit APIs, you want to limit these models for users if they misbehave. So you basically want to cut malicious users, you want to cut suspicious users. And how to do that is to calculate user scores, right? You gather events from mobile applications, from the backend, and based on these events, you calculate scores. Some of these events can be stop factors. For example, if you detect that device is jailbroken or rooted, and it's important in your case, you send this event to the backend, and this is stop factor. We won't send our nice and shiny machine learning model to this device because it's jailbroken. Sorry, no, sorry, right? If the remote device attestation call failed, sorry, this is stop factor, no machine learning model for you. If this device uses some honey token, some honeypots, right? Sorry, this is probably someone tries to attack our nice system. No machine learning model for you. And of course, these top factors and these rules really depend on your use case and your exact infrastructure, right? So things that I'm explaining right now might be relevant for your case, might be not relevant at all, right? Stop factors are very straightforward. If event happened, sorry, the user is malicious. However, sometimes it's complicated to say that, so we have rules, like scoring rules. If this application tries to download URL, and remember we have TTL, URL has expired like ages ago, we track this error and we increase malicious scoring of the user. If the application gets reinstalled really often, say 5 times a day, we increase the malicious score. If application makes too many requests, yada, 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 yada. So for every user, we can calculate a scoring model and change behavior depending on user scores. Just block malicious users, limit suspicious users, and provide a nice service for okay users. Let's mention really quick remote device attestation. Both iOS and Android provides API to do remote device attestation, which means to make sure that application was installed in legitimate way from the App Store or Play Market, right? Check these APIs, Apple Device Check or Android Safety Net. And of course, let's not dive into anti-reverse engineering of mobile application. Just open OWASP MSVS reverse engineering part and follow all these nice things that why it is important to build in our system, because again, mobile applications have these machine learning models, and if someone can easily steal them from mobile application, this is bad. If someone can write and like clone the application that will steal these models and send it to their servers, this is bad. From ML perspective, we can also do some nice things like built-in watermarks, like create those layers, sophisticated layers, or even bind our model into our application only. But this is sophisticated machine learning engineering. Again, I'm not a machine learning engineer. Let's get back to our scheme. The message here is that cryptography is nice. We encrypted machine learning models as far as we can, and then we added traditional security defenses for mobile applications, for API, for cloud storage, for cloud workers. We put this login, monitoring, and our ecosystem is not a black box anymore, right? So encryption is an ultimate security control, and then traditional security controls to support to work in parallel, to work independently. Defense in depth, right? And this is probably the last message for my talk today. Just remember, when you're creating any security system and you're solving any use case, even as simple as protecting machine learning models, failure of security control itself, it's just a question of time. Like failure of cryptography is a question of time, and your responsibility is to build a system that has a lot of the security controls that work together, because the failure of the whole system is how bad your design is, or like how good your design is. As usual, I put a lot of links in my slides, and some of them I will duplicate on this slide, some of them are new here. And my name is Anastasiia. Please, if you have any questions, check my Twitter, check my website, or check our Kazakh Lab site, blog post, or white papers. We write really a lot about cryptography. That's the end. Thank you.
Thank you, Nastya, for the great talk, for the very nice presentation, for firing up day 2 of NoNameCon. I hope we will have some audience feedback. Do I see it? Nothing yet, but experience tells me that, yeah, we need to give people a few minutes.
Just put thumbs up if you like it, like thumbs up the stream on YouTube, so we will know that you watch us.
If you're still with us, where are thumbs up? Oh, yeah, there are some. Quite a few. Okay. Are there any questions? I have questions, but I would like to hear someone else asking questions. There is Peter. Peter will be allowed to talk right now. Peter, please go on.
Morning, Peter.
Morning, Nastya. Jak sprawy?
Very good.
Good. My question is, how do you see this whole development of quantum computing on the matter of cryptography and the way we encrypt nowadays the systems we have and the data we have?
Yeah, totally not about my talk. However, as you know, we already, like NIST already has a competition for post-quantum cryptography, or how we name it, quantum safe ciphers, right? And we have a number of cipher candidates. So ciphers that right now are believed to be okay, to be strong enough not to be broken by quantum computing, right? And in terms of quantum computing, not everything will be broken. So with IS, for example, what we will need to do is just to increase the key lengths. However, TLS might be broken, and that's why many companies right now, like Google, like Cloudflare, they are looking to the cipher to do this key exchange, right? That will be quantum safe. And I really recommend you to read a Cloudflare blog post from previous year, I believe, where they did an experiment of they compared two different post-quantum key exchange algorithms in TLS to check how fast and cool they are. I will try to find the link to this blog post and send it to you. So TLDR, quantum computing will be here not in near future, but we already prepared. The competition for the best post-quantum cipher is happening right now. We will select the best cipher, we will change the libraries, and only systems that will use TLS 1.2 and 1.3 are screwed. Yeah.
Okay, that's good to know.
Okay, do we have any more questions? Guys who moderate Zoom and YouTube, do we have any questions there? Okay.
I see a lot of likes on YouTube, so we are sure that the audience are watching and listening to us. Okay, no worries.
I don't know.
I will have the slide.
I see more likes than watchers. This makes me wonder how it may happen.
They just log in on the different accounts, you know.
Yeah, we have a very creative and knowledgeable audience. Yeah, there is a question, practical one. How long did it take to implement your solution into the application?
Not long, because as you see, it's that defines the implementation. Yes, the design took a couple of months because of this risk modeling, like risk and stress modeling, right? Understanding like threat vectors and understanding defenses, understanding cryptographic protocol. The implementation itself, developers did it in a day. They tested in a day, and then they were doing all this rollout to make sure that users are not affected. So you've seen amount of cryptographic code. It's teeny tiny code. The main things were not related to cryptography itself. The main things were related to the whole approach of changing large ML model into these small individual machine learning models, right? But again, not my area of responsibility. I'm not a machine learning engineer. I'm sure the team did a great job in that.
Cool. There is a question in Q&A section. Let's start with the first one. I hope you will get it, because I don't do it entirely. So is it safe to trust users? It looks like making a wider attack vector.
Oh no, we don't trust users. In this example, as it outlined, we don't trust users at all, and we do our best to, to make attack surface as narrow as possible on the user devices. We use all these anti-reverse engineering measures. So we don't trust users that use jailbroken devices. We don't trust users that use rooted devices. We even don't trust users that reinstall application multiple times a day, right? So we don't trust users at all in this example. And we do our best to not trust curious users, because crowdsourcing is a really nice attack vector here. Imagine that you're a large competitor and you ask users to crowdsource to find their machine learning models and send it to you. This is cool. We don't trust users at all.
Yeah, who does?
No one does.
Okay, it seems that it's rather a suggestion, but I think you might have quite a view on that. So it seems that homomorphic encryption will resolve all machine learning problems. What do you think about that?
I'm not a fan of homomorphic encryption. I mean, the idea is cool. The implementation is quite far from being industry ready. However, recently Google has published yet another open source repository for fully homomorphic encryption, and it's very interesting to dig in. But yeah, let's wait. I think that personally, from my personal opinion, that post-quantum cryptography ready to use will be here faster than ready to use homomorphic encryption fully homomorphic encryption. But fight me, this is just my opinion.
The question from me, will it be ever useful by mere mortals? What do you think? I mean, it's quite a complicated math to make it usable fully. Yeah, there are some machine learning models around that. For instance, network vendors. One of them we can name because it's our sponsor. Cisco, for instance, they have very interesting security detection solutions for encrypted traffic, because it's not like fully homomorphic, but there are like correlations between how malicious traffic looks in clear text and encrypted. Yeah, so you can like derive some knowledge and insight from that, and then basically extrapolate this knowledge to something that you do not know directly and entirely, but you can guess, some details. So it's, of course, it looks more like art than science or technology, but it seemed to work. So will we be there?
I think what you explain is more like a traffic inspection and DLP than homomorphic encryption itself, right? So how
but
to find
you make some derivations, you derive some properties of traffic, not decrypting it, So I think it looks like something very similar, but I provide this example just in order to show that it's not homomorphic encryption at all, but it's some kind of homomorphic themed technology, which is a dirty hack. Okay, let's call it the name. Yeah, it's a dirty hack. But will we be able in the near future to use homomorphic encryption for something provable?
I think that we will stay in this dirty hack area for a long time, because these dirty hacks already exist for searchable encryption, right? So it's possible to build searchable encryption without full homomorphic encryption, again, based on dirty hacks. And one of them is this blind indexes approach. When you take this query, you calculate a blind index, which is hash, and you encrypt the data and you search by hashes. Right, so the data stays encrypted, but you search from it, but you search using hashes. So dirty hack, not homomorphic encryption at all. It's not a dirty hack because it has a mass proof. Well, yeah.
Many dirty hacks have math proof. Okay, another one. How fast will we have quantum computers? Don't we have them already? It's not the same as quantum safe.
We have, but Yeah, I think Alexander, what you're trying to say that quantum safe crypto. We believe that quantum safe crypto will be good enough that quantum computers won't be broken. Well, not in the nearest future. Yeah, but right, when we will have these quantum computers, we do have them already. Check out IBM, for example. However, the trick is that right now we have really small amount of qubits in these quantum computers, and many cryptographers, many researchers believe that we need much larger amount of qubits. Right now we have hundreds, I believe, and we need like 100,000, like millions of qubits to be able to decrypt cryptography. I really recommend you watching a talk by Jean-Philippe Aumosson at NoNameCon last year. He was speaking about quantum computing and post-quantum crypto, quantum safe crypto, and you can find this talk on YouTube, and you can find his slides. And he did a great job explaining when we will have it, what ciphers will suffer, and what problems will remain good and strong.
Okay. Thank you. I think we will have the last question. I think I have a right to ask you one more question. When we meet aliens, what kind of computers they will have? Quantum computers or something similar to ours, like from them and
I believe they're gonna
stuff.
have this silicon life forms, so they might be computers themselves, right? Let's talk about artificial intelligence. Let's talk about singularity, right? Maybe we are building aliens right now with all these shiny things happening in Google Cloud platform with all this code that gets pushed there, feeding the learning algorithms.
Yeah. Okay. Thank you again for the great talk and for being the part of NoNameCon in a new role. It was a great debut. Congratulations.
Thank you. Thank you. My pleasure. Have a great day. Thank you, everyone. Thank you for your questions. And let's continue with talks. Bye-bye.
Of course. Thank you.